I'm going to explore the relationship between work and energy in physics. I've been asked by several students as to how these two concepts fit in. I'm going to begin with the idea of work. So work in physics is basically, it means how much force you need to move something a specific distance. So work is given the symbol capital W, typically, and it's equal to Fd, where F is force, measured in newtons, SI units of newtons, and D is distance, meters. So work is force times distance. The more force you apply to an object, the more work is being done on the object. And sometimes they replace D with little lowercase s for displacement. So I'll draw a box. Let's say there's a box here. I want to move this box from point A to point B. Okay, the distance is the length between these 2 points. That's D. Okay, it's a straight line length. And if I'm pushing it, I'm applying a force F. And when I do that, it ends up at point B sometime later. The box appears here, and I would have done work on the box. So how does energy tie into this? Well, when you do work on an object, when work is done on an object, you're changing its energy. And energy, by definition, a fancy way of defining energy is the capacity or ability to do work. Okay, the ability to do something, to heat something up, to lift something up, to push something, pull something, twist something, and so on and so forth. So that's energy. Energy is measured in joules. And after joules, an English physicist who lived in the 1800s. And energy can be broadly classified into two main types. You've got kinetic energy and potential energy. In physics, kinetic energy is typically given the symbol capital K, and potential energy, capital U. So kinetic energy is the energy of motion, energy of movement. Okay, the word kinetic means movement. Potential energy is stored energy. So motion or movement for kinetic, potential stored. So the formula for kinetic energy, you can actually quantify, you can write a formula for it. It's quite simple. Capital K is a half mv squared. M is the mass of the object, measured in kilograms, SI units, and V is the velocity of the object, the speed in a particular direction, measured in meters per second. So the units for kinetic energy are therefore kilograms, meters per second, or just the joule. Okay, so same thing. Potential energy. So there's different forms of potential energy. There's chemical potential energy, there's gravitational potential energy, and there's also elastic potential energy. We typically deal with gravitational potential energy. U sub G is mgh. They use different notation for gravitational potential energy. I'll write it as U sub G, that's fine. Where m is the mass of the object, once again in kilograms. G is a constant, it's a number, 9.8 meters per second squared. Okay, it's the acceleration due to gravity. And h is the height above the Earth's surface. So here's the Earth's surface. It's the height above which you raise something. Let's say the box, I lift it up 2 meters. Okay, this is h. If the box is on the Earth's surface, its gravitational potential energy is 0 because h is 0. Okay, 0 times g times m gives you 0. So there's a famous law in the universe, in physics, and one of the laws of the universe. It's called the law of conservation of energy. And this states that energy cannot be created nor destroyed. It can only be transformed. This prevails across all of our daily lives. When you flick on the switch for a light bulb, you're effectively using the law of conservation of energy. You're transforming electrical energy from the wiring in your house to light energy in the light bulb and heat energy, sometimes sound energy as well. Okay, so for example, electrical energy gets transformed into light energy and heat energy. Okay, you cannot create or destroy, you can only go between different forms. So in other words, you can't have a light bulb and just expect it to light up on its own spontaneously. This doesn't happen. So how does work come into this now? Well, as I mentioned before, when you do work on an object like a box, you change its energy. Because if you have a box that's stationary initially, it's just sitting there, its kinetic energy is zero because it's not moving, right? V is zero in the formula. But its potential energy, I should say in this case, suppose it's sitting on a table and the table is, let's say, 1.5 meters above the ground. Okay, the box is sitting on a table 1.5 meters above the ground. Its potential energy in this case, U, gravitational potential energy, is not zero, it's mg times 1.5. If you increase one, you decrease the other. If you increase the kinetic energy, you decrease the gravitational potential energy, and vice versa. So in other words, the work done on a system is equal to the change in the total energy of that system being the box in this case. Okay, this is delta, the Greek symbol, which means changing, E subtotal, total energy. And that's equal to delta, the change in kinetic energy, plus delta U sub G, the change in gravitational potential energy. So for any object, it's got kinetic energy and stored energy, potential energy. That's why you add them up to get the total energy. So since work is Fd, and let's say potential energy, gravitational potential energy is mgh, you can equate the two. So in other words, work is equal to the change in gravitational potential energy. And if you lifted the box slowly upwards, there wouldn't be a change in kinetic energy. All the work goes into gravitational potential energy, okay, because it's getting higher above the ground. Let's suppose I now have a box and I drop it, let's say from some height, I don't know, 2 meters from the ground. I'm lifting it, I'm holding the box 2 meters above the ground, and I then drop it. When I drop it, gravity does work on the box, and that's mgh in this case. And this work turns potential energy into kinetic energy. Okay, the potential energy is getting less and less as you're dropping it, and the kinetic energy is increasing, right? Because it's moving at some velocity. So in other words, delta K is mgh. You can equate the two, because when one goes up, the other goes down. This goes up, that goes down. In other words, that becomes minus mgh, and that's minus delta U sub G. Okay, so in other words, the change in kinetic energy of an object is negative the change in gravitational potential energy of the object. So rearranging this, because the total energy of an object has to be constant, or zero, in other words, adds up to zero, we get this delta K. So let's take this to the other side. Becomes that. And that's the law of conservation of energy, and that's how it relates to work.